Yo, what's up, everybody? Welcome back. Today, I want to look at box overlap prediction. Or not prediction, sorry, calculation. My head's in neural network space a little bit. Because we are working on a barcode scanner whose goal is to take pictures of stuff on my phone and turn them into something that is scannable. And we might say, that's an easy problem. We've had barcode scanners since like the 70s or whatever, and I would say you're right to some extent. But there's lots of cases that are hard, and I'm not smart enough to figure out how to parse this. Okay, I'm just not smart enough. And so instead, what we're doing is we're building up a neural network training framework from scratch, working through the process of isolating barcodes from pictures and then trying to basically predict like turn these bars into something that's like easily parsable, like a 96 by 1 array of just like blacks and whites, and like let the neural network learn how to like turn this into like, I'm confident that this is the first bar and it is black, you know? Then once we have that, we can easily parse, using like normal computer logic. Now, where we are at is we are kind of in this world where we're planning on making like a two-stage system, probably something along the lines of my phone camera. I'm taking a video on the screen somewhere, and I'm probably trying to like get the barcode into like some section in the middle of the screen. And as I'm like moving my camera around, positioning it at the world, we might see like a barcode that is like half in, right? Or the barcode is in frame but kind of like blurry because it's like moving because we're like moving the camera, right? And so we in these cases, we'll do a bad job at the second stage, where once we like find the barcode in here, we're like, oh, okay, so this barcode is like here, and we can like extract that thing and turn it into something that is like aligned with our viewport and kind of like approximately the size of the field of view. The thought process here is that we don't have to do as much thinking and we can work faster if we start with an easier problem that is the bars are always approximately in the same spots, right? So because of this, we need to make sure that if we predict a bad box, that we don't use it, right? So there's like maybe the box looks like this, and our network, it's like blurry or something, and so it's like because it's so blurry, finding the orientation of the bars is like harder than usual, and so the network kind of like freaks out and it predicts like this box instead or something. We need like some system that says don't fucking use that. Do not use that. That is bad. It will not work, right? And so we're taking a little bit of inspiration from this like YOLO V1 paper. It's really like the only paper that we've read so far. But it's like kind of old, but it kind of gives us like a bunch of ideas on how to work with like convolutional neural networks and stuff. And it's like it was a hit back in the day, so it's kind of like a good place to start. But they do this thing where they get the network to predict how good of a box it made, right? So it actually turns out that it knows that if it did a bad job, it kind of like can guess that it did a bad job, right? It could be like, oh, my gradients, sorry, I'm looking at the wrong thing. Oh, my gradients that I used to calculate like which orientation I'm supposed to be, they weren't very strong, and I know that they're not very strong, which means I probably calculated a pretty bad box. And so like I can tell you that. And so what they do is they calculate confidence, they call it, and they express the confidence as a predicted value that is trained to be the same as the intersection over union. So if I have two boxes like this area here is the intersection, the union is like the sum of the two boxes, minus the intersection, right? So the idea here is that like this whole area intersection, and then the union's the part that is the same. And so the idea here is that if your boxes are perfect, the intersection of the two boxes, union is the two, intersection is the part that overlaps. So if you're here, your intersection over union is like 1.0. Mwah. Very good. Very good, right? But if your thing is like this, you've got like a box that's like a little bit worse, maybe like this. Like the intersection over union is still pretty high, right? Because like this intersected area is like still pretty large relative to the area of the two boxes. And if you have something like really fucking bad, right, like this, intersection over union will be quite low, right? And so they say, use intersection over union, use that as a prediction target, it will learn it okay, and you can use that as like a confidence value. So if we want to do that, since we're doing everything from scratch by hand ourselves because we hate ourselves, we need to figure out how to calculate this thing. Right, and it turns out that it's like, if you look at, just looking at this example, it's like, oh, this isn't like super trivial, right? Because the intersection is a 1, 2, 3, 4, 5, 6, 7, 8 vertex polygon that we have to somehow find. And so I was just like Googling, I just Googled like rotated IOU, because this is a thing that people do all the time. And I clicked this link and I read this a little bit. I didn't really read it too carefully, but this guy talks about this Sutherland-Hodgman algorithm, which seems pretty reasonable to me. We can explain it by looking at this picture. So they're saying, hey, we have a polygon here, and this W, this other polygon. And this is like a more complex case than what we were trying to do, which is just like 2 boxes. But, you know, the idea is still sound, where they basically say, hey, just like walk over each of the edges of this red polygon, and like take like your outside and inside edge of this thing, and consider anything past the outside edge as like no good, right? And if you just like walk all of, and if you intersect with this edge, we'll like add that point. And if we just walk all of our edges, we will eventually find the right thing. We can go through an example because it's like a little bit easier to show here. So say we had box 1 and maybe like box 2, like this, right? Yeah, box 2, I guess. We pick one as the clipping polygon and one as the, like, I think call it like subject and something else. I don't really fucking remember. They call it like subject polygon and clip polygon or something. So one is clipping the other, right? So we'll say that we're using this guy as the one that we're like doing the like bounds checking on, I guess. They're kind of saying like you take this plane and you look at any vertices outside. So this vertex, boom, no good. He's on this side, bad. This guy, also, delete this shit, delete this shit, delete this shit. Right? But then you only have one vertex. So like, what do you do with this? Well, you find the intersection of where these lines intersected and you add these points back. Right? So that's like only with this because it's like only overlapping on one edge, that one edge kind of like already determines this polygon, right? So now you have a polygon of these 3 points and those are the intersection. Great. Let's think about like a more complex case maybe. So we can run this experiment a few more times. Experiment is the wrong word, but we can run this a few more times. Like say we have something like this. Bing, bang, boom. So here, our intersection is here, right? That's what we're trying to find. And so again, we do something, we take this plane here, nothing to delete, right? Great, that's fine. This plane here, delete this vertex, delete this vertex. And then what do we have to do? We have to add some back, right? So again, we like extend this plane forever. And we find that on these vertexes we deleted, if we look at like all of the edges here, we'll notice that there's like an intersection point here and an intersection point here, right? Okay, so now we go onto this edge here and we do the same thing. So we nuke this or these guys are already deleted. We have these points now. We delete this point. We delete this point that we just added because it's out of bounds. But we kind of snap these back, right? So then we have a point here and a point here. And then we do this last edge where we do here, we delete this, but then we bring them in here and we have like this polygon here. That's kind of the idea, I think. And apparently this works like generically. We're going to have to like experiment and see. So I think the plan is to like try to do this in some way and then visualize that it's correct. So we in the pre-stream segment created this like little GUI where we have just 2 boxes, you know, X, Y, width, height, rotation, and we can just kind of like manipulate these however we want, right? And I'm hoping that once we have this thing calculating, we can just kind of like show it on here and see how it looks. And if it's good, it's good. So that's the plan. That's the plan. Let's see if we can make it work. I think before we get into like deep into the nitty gritty though, we have to figure out how to calculate line-line intersection. I haven't looked this up yet because I assume that we can figure it out. But, you know, that's one part of this is, you know, we have some infinite plane and some line going through it. We have to find this intersection point, right? So can we think about this? So I guess we have a box, right? We have a box. And he might be any orientation, right? He might be like this. And let's say that we are trying to find if this line defined like this goes through this line, right? What do we have here? I'm assuming there's something dot producty to do here. I'm assuming. So we're gonna try to like work our way that way, but I don't really know. So I guess what we are trying to find is there's like this triangle, right? And this triangle looks a lot like some sort of okay. So if I want to draw this a little differently, okay, let's draw this line instead. I think that'll make it a little easier. So if we extend this line like this, so that we have a right angle triangle here, this angle, we have like a little, we have a cosine here, right? We have adjacent here, hypotenuse here, A, B, like we have, so this, if we define like this, A, this, B, we have like AB cos theta, which is our dot product, which is like very nice. There's like a projection here, right? So the dot product is defined a couple ways. One is like if you have this line and this line, it's kind of like a you can think of it as like the projection of this onto this. So you can think of it as like this distance sometimes. You can also think of it as AB cos theta, where A and B are the lengths of like this line and this line. You can also think of it as A dot A plus B dot B or something, which is really cheap to compute. So that's why we kind of like to do things in terms of dot product. So I assume here that if we have this line and this line, there's this triangle that we can leverage. We calculate, I guess, if we calculate the projection or like if we calculate this distance, which we can easily do, then we have like this point, and we can add that distance along this vector to that point and find out the intersection point, which I think is what we're trying to do. That sounds right to me. That sounds right. Fuck it. We'll see if we can make that work. Okay, so can we do something here? Let's just start by doing like line, intersection. Okay. And what do we have here? I guess we have like I guess we need like a line who has a vec2 and B. So this is like how we define one line. I don't think that's going to work too good. Maybe. I don't know. We'll see. So then we have like a line B as a line, and this returns a vec2 as the return thing. We want to calculate the direction of these lines, probably. So hold on. We have to think about this a little bit. So this line could be like anywhere along this, right? We have, I guess it's like, I think we're missing something here. We're missing something. I don't know what yet. So we know this angle. We definitely could find this angle for sure, because we have like direction of this vector here and this line here. So that angle is definitely knowable. And we know that we have this right angle triangle that we can work with, given this angle. And so surely this distance is like just knowable from that. Because we have, no, right? Because like it depends on the scale of this thing in some way. Yeah, from just the angle, we only know the ratios of these, which I think that we're not hitting? Why should it be right angled? Because we're just like extending projection forever, was kind of what I was thinking. But now I'm like less confident about that. I'm less confident. I'm thinking. So how, again, the goal is to find this. I am positive. Yeah, I guess I'm missing something for sure. Definitely missing something. I don't know what the fuck you're talking about, but I think that I'm gonna delete a message that where you're talking about being happy that someone died. I don't know what the fuck you're talking about, but I'm just gonna delete that. Yeah, I think there's something here. I'm missing one piece. One piece. Yeah, because this line could be literally anywhere. So I think that, yeah, what am I'm missing, it's probably something more like, you probably need this line or something. It might be something like this. So you have this, you have this, you have this. These points are useful in some way. They have to be, right? I guess we have this. We can project this triangle and this. Then we can project. Maybe this is it. So we have this segment and this segment, but I don't know if that helps us at all. Hold on. Let's get a little slantier so that we can visualize better. Really slanty, and then like, can we bring this like even like back or something? So we have this. There's a right angle here for sure, so we can easily calculate this length, but then we're missing this guy. There's also like this triangle, which is useful, maybe in some way. No, I don't think so. Huh, I was pretty confident we could get here. Okay, I think it would be easier if these lines were smaller. Okay. So we want this line and this line or something. Okay. So we obviously have this and this. We have this line here, which lets us project, the rest of this thing. And can we find, so is there a triangle we can make somehow that gets us here? That's the question we need to answer. Probably there's some triangle that has a right angle here. Right? There's a triangle here. There's a right angle triangle here. But we don't have this point yet. Okay. I feel like this triangle, my gut says that this triangle is nice. That's what my gut says. Oh, because we have this triangle overlaps with this triangle in some way, I think. And Yeah. There's something here. Not sure what though. Not sure what. So this section is really easy to find. This section, easy peasy, super easy peasy. Then this is also super easy peasy to find, but I don't know if that helps us at all. Because what we really want is like either this line. We really want to find like this line eventually. That's kind of like the holy grail here. Oh, we have this length though, surely. Which means we have this point. Which means if we have this point, surely this is findable. Surely. If we have this angle, which is the same as this angle. Yeah. Yes. Pretty sure there's something here. You don't need angles at that point, you have the dot product. Yeah, but sure, the angles are like dot product angles, same, whatever. Yeah. Okay. So we find this length easy. So we'll call this A1, A2, B1, B2. This is, we'll call this C. So we can find A. All of these are like gettable. The last piece here is just this length here, which feels very doable. I'm just not quite sure how. This is a right angle triangle here. So it's like cos sine theta. No, tan theta? Ew. Tans are gross. Is equal to like B2 to C over, you know, what we're trying to find. So you can flip those. But there's probably a way to do this without tan. Probably. Stop with the trig. I mean, this is all, it is trig, no? Dot products are still trig. You're just thinking about them slightly differently. But like, what are you suggesting? You're suggesting that there's some dot product I can use here? I'm just not seeing it. I'm not seeing it because I'm missing. Dot products are not trig, they're linear. But like, what are you talking? But like, dot products are. Whoa. Dot products are just AB cos theta, right? So like, you can like find them in either space. I mean, like the like linear algebra, it's like you're just doing trig just with less steps. No, like any projection you're doing, introducing a project, you can be interpreted that way. Yeah, that's what I'm saying. I don't know how you're supposed to think about these things if not, like, the angles are important, I would assume. Like, there are projections somewhere, but I need to find them somehow. So I don't really know what you're suggesting. I guess like there's probably some sort of like ratio bullshit. So you know the ratio of B2 to C versus this point. We'll call this D or something, right? So you know B2 to C is some ratio of B2 to D, which means that there's B1 to D. This is the same as like the same ratio of this. Yeah. That's probably that's the unlock, I think. I think that's the unlock. So you do this dot product to get this line, A1C. Then you Pythagoras to get B2C, probably. Then you have B2C as a ratio to B2D. And you use that ratio from B1D. That sounds right to me. You're saying the lines I need is A1 to C, C to B2, and B2 to A1. No. No, you haven't listed B1 at all, and B1's like a crucial point to this thing. B1 has to be in the equation. Otherwise, you could put this anywhere, and like the line would intersect. Like you can immediately tell that you need B1, because like if B1 was here, your answer would be different. So I'm pretty sure I'm right. You mean B1 philosophy? Okay, cool. I think I get it. So let's just work through. Let's write it down one more time. So we have A1, A2, A1, A2, B1, B2. Easy. We do triangle of A1, B2, C, we call it. We do dot product of this. One of these guys has to be normalized, probably. Right? Because it's it's like L length 1, length 2, cos theta, which means that like we're looking for opposite cos theta is, adjacent over hypotenuse. So then we bring like the h here, we get a adjacent here. So we need A1, A2 to be normalized here. So it's like dot B2 with A1, A2 normalized. This gets us this distance, hype, which gives us A1 to C. Then to get B2 to C, it's maybe we should create some names here. We do Pythagoras though. So it's like this, we have this distance squared minus this distance squared is this distance squared. H squared minus adjacent squared or something. This is this distance, and then we say BC is this, and then we say like ratio is BC over BD or whatever. Then we have this ratio, and then the answer is like AC minus. Okay, let's use more letters. If we use more letters, our life will be easier. A, B. Okay? C, D. Easy. E, F. Here we go. Fucking finally. Okay, so we have AE is equal to the dot product with AC and norm AB. Easy. Easy, easy, easy. Now we have AE. We're trying to find CE. So we have CE is the square root of AC times AC plus AE times AE. Easy. Okay, so we have this length here now. Now we say CE over CF times DF is, we'll call this X. This is XE. Easy. So then AX is AE minus XE. And so the point is the norm of AB times the length of AX. Easy. Easy, easy, easy. We fucking got there. Holy, that took 30 minutes. Okay, now we just have to turn this into like code. So let's figure this out. So we call this, I guess we'll call this L1 and L2, and we'll have to draw this picture in comments later or something. But it's fine. So I think we have some sort of like normalize. I guess. Okay, we have like AB is L1B minus L1A. Okay. Then we have const AB norm is normalize AB. We have then I guess we just have like AE is stood math dot AC, which we don't have yet. So this is L1. Okay, we need like A is L1A, B is L1B, C is L2A, and D is L2B, because otherwise I'm gonna get lost. Okay, easy. Okay, so now we have this AC. Cool. And what did we say we're gonna do with this? It was like take the magnitude of this thing. We have length squared of this. So AC2, like this, is the length of this thing. And we said we were gonna take the square of that and the square of CE. Do we have C? We need point E still. So this is, I guess, AB norm multiplied with this thing, I guess. This is the line for AE. Okay. Which I think I don't really care about, to be honest. I think I just want like AE len. So AC len 2 and AE len 2 is AE len times AE len. We've got our two squares. God, I'm sure that I'm doing this stupid, but I got there by myself, so there we get some points for that. And then what did we say we were gonna do? Is that we were gonna take. Do we have F? How do we get F? It's like we project CD onto CE norm. Which means that we need E somehow. So E is AB norm times AE len. Yeah. Yeah. We like multiply the distance along this vector of this thing. Now we have point E, which means that we can now find CE is E minus C. We have CE norm is the normalized version of this thing. Cool. So then we project CD. We do a little projection here. So we're doing CD onto CF, or CE norm, I guess. And this is CF len is this guy. And then we can do the ratio is like the like small try ratio is CE len over CF len. Which, do we have CE len? No. Stud math length CE. So that's this over this, and we should be able to find xe now. Somehow. We need to project the other way or something. Is this line parallel with this line? This is right angle and this is right angle, so yes. It has to be. So df is the projection of DC onto this line. Yeah. Something like that. DF length is the projection of backward. Like we have CD, so we can do CD over negative AB norm or something like this. Sorry, this is a dot product, I think. I'm pretty sure that that's right. So we're it's kind of like we've got this line now, and we're projecting this onto that, which is the same as this, because this and this are going to be the same length. Pretty sure. And so now we're basically there. XE len. I'm sure that there's some sort of like negative shit that we're fucking up here. Yeah, this shouldn't be negative. Maybe it should. I guess it depends on like... It depends on which way things are facing. So it's likely that these like anything that we have like len, we might want to be throwing abs on here. Otherwise we'll be wrong about it. If things are backwards, probably. And so now XE length should be like DF len over small tri ratio times small tri ratio, probably. And then AX len is... It's like... AX length is AE len minus XE len. And so that means X is AB norm times AX len. Okay, that's something. AC doesn't exist. Norm. AB norm here. He doesn't like this for some reason. What doesn't he like there? Why do some functions zig start with that? They're like built-in functions. They're built-ins. So they're not functions calls necessarily. They're like the compiler will like replace these with something, whatever it wants to, type shit. AE len is unused. Did I not need to use these to get CE? No, I did not, because I just used the dot product. Of course. Of course. Okay. That's like a maybe. We can test this by rendering this point in our visualization by looking at maybe the top two lines in our boxes. I'm in the wrong thing probably. I don't know why the fuck I implemented this here. We should be in box. Here we go. Okay, so we should be able to be like line, intersection, given A is on the first line is maybe box 1 top left, and B is going to be top right, and then we'll do another line here, which is using box 2 top left and top right. Intersection is this, and we need like a top left and top right function on this thing now. So can we do like function top left returns a vec2, and he looks at his center position like this, center. He's got his, so he's gonna be like x-axis, I guess, is gonna be cosine of rotation, and the y-axis is gonna be the sine of the rotation. So we have like, no, sorry. Yes. Yes. No. X-axis is the vector 2 of this thing. Yes, that makes more sense. So he is pointing like, if I am rotated, you know, my box is like this. God, that's not a picture. My whole x-axis of the box is rotated by this angle. So this is sine y cos x. Okay, so then we have y-axis is like, do we even need that? Yeah, we do. This is, so I always have to draw this. If I have this and I'm rotating to this angle and this angle are the same, so the y-axis becomes negative sine, positive cos. So this becomes negative x-axis 1 and x-axis 0. Okay. So we can use these to be like center plus x-axis times width over 2. Yep. Plus y-axis times self-height over 2. Yes. But these are probably minuses. Y is positive to go up, x is negative to go left. Okay. Ew. Fucking types, dude. All right. And top right is the same, but with plus plus probably. Okay, then we have this intersection and we can just render this thing. GL. I guess we need to like put this thing in a buffer and then render that buffer. I guess is kind of how this works. Point buff, point source, bing bang boom. And then we need like a point buff that we render at 0, 0 by default, maybe. Something like this. Okay. What is he pissed about here? Did I forget squiggly? Yep. And then here, this is point buff. Point source comes from point buff. And then we say that the point buff bind, like update buffer with v pause is equal to intersection. Okay. And then we can call gl render points. Maybe it's GUI state, solid color renderer, render points, which doesn't exist yet. God damn it. Render points. Which doesn't exist yet either. Render points with GL points. Okay, so now we can call render points somewhere with a point source. Easy. What's this guy pissed about? Forgot some squigglies here, probably. Point buff needs to be a variable for this to work. And this thing doesn't have try on him. This guy does? No. This guy's like, give me a color and a transform. Oh, we could have just used the full thing. Oh, we could have done this with the transform. Fuck. But whatever. Whatever. Transform, identity, and color is, I don't know, green? Or something? Alright, let's see if that, like, does something. Bad news bears. I do not... Oh, maybe we need to do, like, GL point size. Before we do this. Yeah, okay. So we have a point there who is definitely wrong. Okay, let's get the rotation down to 0. And so we are expecting this thing to be up here, which we have done terribly wrong, or our top left and top right are wrong. Both of these are very possible. We're doing something terribly wrong though. So I guess let's just start by rendering out things that we think we should be able to do, right? So if true, let's just return A for a second. So this is already fucking wrong? That's crazy. Which means that our top left, top right must be wrong? I don't know how though. You get those by using the 2 points that are on the line? Yeah, I understand. So like if I just return A, like the green point should be on a corner. And he like kind of is like in the top left. It's probably just like top left times 2 or something because OpenGL space. Yeah, OpenGL space. It's probably like, oh wait, then our widths, maybe we're just rendering the boxes wrong. That actually seems more likely, right? So it's more like there should be over 2s here, probably. Let's see. So if we have our width as 1.0, 2.0 is the width of OpenGL space, right? So that looks more correct. Okay, so now the green dot is right fucking on the line, which is good. So let's, maybe what we should do here is for a second, return a bunch of points and render them all. Probably. I don't understand labeling. Yeah, that's fair. Oh, you're not talking to me, you're talking to Christoph. I don't even know what you guys are talking about, I'll be honest. Okay. So can we return for now, like 5 points? 7 points? Well, A, B, C, D, E, F, red. This is what we're trying to return. And we want to render them all. For a second. So for P in intersection, we're doing this. And I guess in reality, yeah, it's fine. It's fine. That's not really how you should do this, but F doesn't exist. All right, fine. Fuck it. A, B, C, D, E. Fine. We'll render 6 points. Fuck you. Okay. So it looks to me like this point, this point, this point, this point are correct. And then like our return point and somebody, this guy, point E, which is supposed to be like really easy for us to find, seems like fucking broken, right? He's supposed to be like here. He's supposed to be right here, right? Because we do like this projection, or maybe right here, depending on which order these lines are in. So what the fuck are we doing here? We're looking at A to B times AE len. I need the picture again. AE len is the dot product of A to C onto the norm of A to B. AC, AB norm, AE len. Oh, this should be A plus this, I think, right? We start at A, then work towards that direction. Yeah, okay. Somewhat. I mean, it's still wrong. I don't really know why this is not doing what I expect. Can we... Oh, wait, maybe this is right. This is going from this point to this point, projecting here. Which is confusing because, oh, this rotation is maybe fucking things up. No, this is 0. So I would have thought, based off my understanding of everything we've done, that E should be here? Because this should be... Oh, am I looking at this? I think I have my points flipped. Okay, let's take a look again. Okay, so this is doing what I expect, right? So A to C, then we go down here. Great. That's starting somewhere. So then our return value is wrong because we need to do this is relative to A again. Oh, wait. Wait a sec. Look at that. I think that's right. Hold on. Let's render the points bigger and on top. Yeah, look at that. Look at that. Too big now, though. But I'm pretty sure it's right. Pretty sure it's right. So here we can see this point right here seems to be kind of following pretty well. And then if we go past, he still shows up. Looks like he kind of falls the fuck over if both of these pass, which indicates that there's some sort of like absolute value thing that's not working correctly. Yeah, what's going on there? It's like if C gets backwards behind the direction of A to B, then we have a problem. Let's double check whose problem though. Okay, let's go up here. And we move this guy past. So it's E flips over. Because AE len I applied an absolute value that I probably shouldn't have, actually. It kind of evens itself out. Okay, that seems like it's tracing pretty well. It looks like if my... Yeah, it looks like there's another absolute value there that's not supposed to be there. I don't want to see, like, maybe I was, like, overcooking it. No, something's backwards now, and it was because it was our CD length. We probably had backwards. DF length was CD on AB Morm. It should be DC, not the other. It should be the other way around. Okay. So this here. Yeah, so this point here is like if this line continued forever, it would intersect there. So that does seem kind of right. If we like rotate, we see it kind of come back and around. Yeah, I think that's working. Took a minute, but we got there. Okay, so we have line intersection. We might have to do some clamping here, but it's fun for now. Okay, let's go back to only returning our return value here. Just double check again. Yeah, that's great. That is great. Cool. So all of that was like just step 1 in whatever we're doing next, which was this algorithm where we iterate line by line on one guy, and we like nuke vertices that are behind us. Okay. So we have, I guess, can we just do one iteration of this thing as stage 1? I think that's the play. So let's draw something. So we want to do something where we take this, and let's say that we have this guy, right? Easy. And we want to draw the overlapping part. So step 1 of this is we take this line and we want to know like inside points versus outside points. So we want to, I guess, we look at like each point on this polygon, and we say, is he on the left or right of our line? Which I guess is like dot product with the like 90-degree rotation, probably. Yeah, so like I guess we take this line, project it onto like this axis, and if it's negative we discard it or something. You might be able to do something like a cross product here, but I don't really remember those as well. Do they mention in here? No. Cross products only work in 3D. Yeah. What are they telling us? They're like, I need to look. I mean, you can just imagine the third dimension coming out of the page. It's like the same shit. It's like the same shit. It's like, which way are we oriented one relative to the other? But So does that help us here? It might. I'm just gonna do it the dot product way though, because I can like visualize that in my head really easily. Okay. So I guess let's start by rendering points that we think are inside or outside one of our clip planes. Okay, let's start there. So inside, like, point should discard clip vertex bool. Should clip vertex. And we have some plane, so defined by a line here. Point. Like this. And it's like, okay, what do we say? So we're assuming that we're going clockwise probably for now. So we're inside if it's on my right, if this is A and this is B. Right? Yeah, something like that. So we have like line B minus line A gives us this vector. We rotate it by 90, so we just flip so if we were going like 0 1, we want -1. If we want, this is 1 0, we want 0 -1. If this is 0 1, we want 1 0, right? So we move the y to the x and then we invert. So we say like, you know, rot 90 axis is stood math normalize. We take the old y and put it in x. This is AB, so it's AB 1 and negative AB 0. I think. Then we have this axis here, and we take, like, we just dot A to the point. And we put this on the axis. And we say, if this is less than 0, then it's bad. This seems right to me. This seems right to me. So can we then render whether or not we should be clipping stuff? I think is the easy thing to do here. So let's take all the points from box 2, which means that we need, you know, I mean, this is stupid for now, but whatever. Bottom right is plus, minus, and then bottom left is... We're doing, like, way too much math here, but it's fine. Negative, negative, okay. Cool, so can we take all 4 points, check if they are left or right of some line, and then see what happens? So we have, I guess, like 4 points is, I guess we'll look at box 2. Top left, box 2, top right, box 2, bottom left, box 2, bottom right. And then we will say like 4 points, P, if we should discard it, I guess. Should clip vertex based off of, I guess, like A is box 1 bottom left, to top left. And we're like, should we clip these points? And if we should, let's render that thing as like red or something. Okay. And this thing probably needs like to know that he's a bunch of vectors or something. Okay. So what the fuck is going on here? Oh, I'm rendering the wrong point. I see. That would do it. Okay, so we're pretty sure intersection's correct now. Okay, so here we're seeing if things left of this line need to be clipped, then... I mean, looking at where the red dots are showing up, I'm pretty sure this is right. I don't know if you guys can see that very well, but like we can see that like it's this line here, right? So as things kind of pass that line, they kind of become red dotted, right? So I think this looks like it's behaving correctly. Looks like it's behaving correctly. So that's part one of this thing. So first, I think that the algorithm is the next thing we want to do here is we clip those things. We start with the box. We start with the other box. So let's say we have a thing that's like calc intersection for now. And he takes box 1, box 2, and I guess he returns a list of up to 8 points. So I guess for now we'll just make an alkyd thing. And this is going to be some amount of points. Okay? I guess yeah, we do like we have like some array that is up to 8 points, I think, maximum. We'll see if that's true, but I believe that's true. Okay. So first, we start by doing like, hold on, this thing could fail. We start by appending all of the points in box 2 in clockwise order. Top right, bottom right, bottom left. Okay? Cool. So these are the points. And for each edge that we are looking at, but we will start with just one edge. So we will call this a line from box 1. I guess really like this should have like functions to get lines, right? That'd be kind of nice. So if we have like function left and he returns a line, he returns like the clockwise thing here. So it's like bottom left and B is self top left. Okay. This is our left line. So here we're going to be like B1 left here. And I want to see that this guy iterates over all of the points in ret, clip edge here. So for ret items, we start by removing things if they fit. It's easier to double buffer this, I think. Because then we can copy from one to the other without worrying about like modifying in place. Yeah, can we do that? Can we do that? I feel like that's easier. In index, maybe do out index. And we do like ret 0 append here. Let me do this. Okay. So in index is out index plus 1 modulo. And so we iterate over, for here, we start with like ret out index clear. Nuke that shit. Nuke that shit. And we iterate over in index here. And for each point, we just say if should clip vertex given our clip edge and p. I guess if we should not clip this, we have ret out index append p. He's totally chill. But then we also have to look at the line, right? So here, these things are supposed to be clockwise. So we also look, okay, we need to draw it. We need to draw it. Wrong thing. So here, I am this box. I am this edge. I am looking at these points, right? 1, 2, 3, 4. I guess it's literally just like if there's an intersection, I add it, right? Even if that intersection is out of bounds of the line, as long as it's in bounds of this line is all I care about. I think. So we have our clip edge here. We say discard this point and this point. And then we look at these two lines and check if they intersect this thing. Cool. So I guess we have like intersection line is going to be like it's going to be a line where the first part is at our point and B is just the next point. And this has to be like modulo the length of the list because we're assuming like a closed loop here. So something like this. Just an absolute fucking disaster. Just a fucking disaster. But now we can do like calc intersection. Whoa, line intersection of our clip edge and the intersection line. And I guess this thing could be out of bounds of this line too, right? So we need to check if that point is on this line, I guess. So if point in bounds of the intersection point on the intersection line, if this is true, then we add the intersection point to our output vertices. I'm pretty sure is what is supposed to be happening here. I think, right? Because like what we're trying to do is we're trying to take these two vertices and delete them and then add these two vertices where these lines intersect. Those are arrays that can change in size, right? They're clamped at 8, but yes. Yes. Okay, so point if point in bounds or something. Point in bounds. So we have our point and our line. Right? Yeah. And so how do we do this? We have like a point. We know it's like on some line. It might be over here. It might be over here. And so I guess it's just that like if this length is greater than 0 and less than this length, right? So this is point minus line A. So I guess we can calculate length squared. I think that doesn't make a difference, which is cheaper. AP len 2, and then we have AB len 2. Okay. So just like return AP len 2 is greater than 0 or equal to 0. And AP len 2 is less than AB len 2. Yeah, sure. Okay. And we should just be able to return these points for a sec. And I would love to see if we try to calc intersection now on box 1 and box 2. Calc intersection given probably scratch allocator. Box 1, box 2. For intersection points, can we just render them in green? For now. Try here probably. Why is this guy mad? Probably because I have to try here. Okay. So I'm not seeing jack shit here, which seems bad. Seems bad. Intersection points. What am I doing wrong? It's empty. Why is it empty? Why is it empty? So we take ret 0. This is backwards. That's why. Much better. Okay. So what are we seeing here? So I think that the left edge is what we're working on. So anything that if this passes the left edge, then we see a good sign here that this point goes away, right? And these 2 points show up. Open the terminal and type history pipe sh. No, that's insane. So I guess the problem here is that it looks like our like in bounds checking is wrong, right? These 2 points should not be here, and these are the intersection points of this line here and this line here probably. So what point in bounds? What do we do wrong here? So we have a point. I guess I'll just delete that message, and I should ban you, to be honest. But I guess I'll just delete the message. But don't be an asshole. Better to do sh bash history. Yeah, you're good. You're good. I know that you're joking, but the other guy, he's like didn't seem like he was joking. Okay, so what have I done wrong here? Point in bounds. Oh, because we're fucking using length everywhere. I'm an idiot. Yeah. This should just be... Can we just do like dot product of AP onto AB? Do we need to worry about lengths here? I don't think so. I think that even though these are non-normalized, we do need them to be normalized because we want to check if they're out of bounds on both ends. This might be overkill, but this will work, I think. Which is all I really care about for now. So if this is dot is this, and if this is greater than 1, if it's less than or equal to 1 and greater than or equal to 0, then we're in bounds of the line, I think. This, I feel like I'm doing too much math here, but still no bueno, huh? He's still doing the same shit. Am I crazy? I kind of think 1 should not be normalized. Yeah, I agree. Intersection point, intersection line. Okay, so we're like, give me this clip edge on this line, and I want to check if this is on the line. Okay. So, dude, am I fucking mental? It's literally like point A. So we have option of like P, A, B. Right? So we have AB here, AP here. The dot product of one onto the other should be negative. Can we maybe log these things? Oh, wait, can you just wait? I'm also kind of stupid. I don't think you need this dot product, right? In any scenario, other than completely vertical, you can literally just look at one axis, which isn't great. AP and AB are parallel, so their dot product is 0. Is that true all the time? Isn't their dot product... Isn't dot product 0 if they're perpendicular? Right? This is... I thought that it was like, you know, projection 1, right? So if they're parallel, it should never be 0. It should always be either negative or positive. And I don't understand why this isn't working then. Maybe we look. If D is less than or equal to 1 and D is greater than or equal to 0, which feels right, I guess std debug print point line D. Let's just we got a log because we're too stupid to figure out what we've done wrong. Point line dot product. What the fuck is going on here? Okay, first of all, let's try to get like a degenerate case here. So here we have two, it looks to be two guys that are wrong here, right? So point, oh, -1, 2.27. So here we are -1.5 here. X is between these two numbers. So our dot product is good. -1.5, 6, 3. So this should be false, right? I think. If the point is -1.5, negative, oh, sorry, it's -0.15 and -0.86. Here, we have the line going from 0.6, -0.1. Oh my god. I know you need to fucking draw it. So we have -0.15, -0.8. So like kind of like down here. Then we have 0.6, -1. So kind of like here, -0.1. Then this is 0.4-ish, -0.3, right? So we kind of have like this, right? So you have like this line and this point, and he's saying dot product is like almost 1.0. So like, why the fuck? Oh, because we normalized both. And if we normalize both, it will never be above 1. That's why. So we want to be like, in the direction of AB, how far does AP go on that thing? And is that larger than the length of AB? Yeah, that's what we want. Length, AB, then we do AB norm is, AB norm is AB. Yeah, here we go. AB, so this is AB over as a vec2 normalize or length splatted. Yep. Then we dot product onto AB norm and we check if this is less than AB len here. That makes more sense. All right, look at that. Look at that. So here we see this left edge is kind of cutting out any vertices that are past the left and adding the 2 on the intersection. So that's really good. That's really good. Okay. So now we just have to do this for every line, right? So we have left. Let's just fucking make all lines here. Right is R's here, and probably swap order because we're trying to go clockwise. And then top here is going to be top left to top right, and then bottom is bottom right to bottom left, I think. And we just do all 4 edges. So we say const edges is a bunch of lines, which is going to come from B1 left, B1 right, or top. I guess maybe it doesn't matter. B1 right, B1 left. Okay. And then here it's like 4 edges, clip edge. And we do all of this. And I think the only piece we're missing here is that we need to adjust our out index. Because we're flip-flopping between 2 vectors. Uh-huh. Okay, so we fucked something up. Okay, let's start by just doing 2. So we'll only look at left and top now. I don't feel like this is doing what I want it to do. Probably because we're off by 1 here. Oh, our in index has to change as well, huh? And I think we want to do out index here so that the out index is valid when we exit the loop, which means that we start this at 0 and then he becomes 1 at the first entry. Okay, so this looks right. So there's our polygon. Then I kind of bring this guy down. This is, oh, we're only clipping 2 edges, my bad. Top, B1 right, B1 left. Okay, let's see if this is all right. Oh, that's really promising. Okay, so here we have this triangle here. We kind of come up here. Now we have points here, 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 and here. I go up a little farther. This is still an active point because it is in the red polygon. So the intersection looks good here. I come over to the left. Oh, hell yeah, dude. Look at that. I think this looks like it's working. So what we should do now is render the intersection area so that it's easy for us to tell a little bit, make it a little easier for us to tell. So we need to take this polygon that we've generated, and I think that we can assume that it's a convex polygon. So I think that like no matter what box shows up, I think it's valid to take the average of all of the points and then do a triangle fan like this. I think that this will always work. I think. We'll see. So here, I guess we get the polygon. It comes out of this thing. And we say average is equal to, is a stud math vec2 of 0. You have 2 left feet. Do you type left twice before? Thank you. Thank you, Travis. Thank you. Much appreciated. I do have 2 left feet. 4 intersection points. P, we do average plus equals P, and then we say average divide equals intersection points len, probably. So now we probably have like an average thing here. I don't know why he doesn't like this. Cannot assign to constant. That would do it. Float from int. And then what are we fucking doing here? We're making like a triangle fan. So we want to do we want this buffer. Okay. How does triangle fan work? OpenGL. Dude, I like how it took us like an hour to do I like how it took us an hour to do line intersection, and then it took us like 30 minutes to do the rest. What the GL draw arrays. This is what I'm looking for, right? We have triangle fan. And does it tell me like the fucking vertex order? Hello? I don't want like some, okay, is it this? Okay. First vertex will always be held fixed and then the rest of them go around. Okay, cool. So do we have render fan? No. Render fan, and then render points. We just do render fan with GL triangle fan. I should be thanking you for humoring me. Okay, so here our thing is like GL buff is going to be if we just do fuck it. We want average, and then we want to like concatenate this list with the other one. So we want like GL buff is a stud util runtimes bounded array of probably like XYT program vertices or something. Yeah, that sounds right. This goes on our scratch allocator, and this is like 9 long max is his maximum here. We go like GL buff push or append average, easy. And then we go like 4 intersection points. This gets this point added. And then we update our buffer with GL buff items like this. And we then render a fan. Okay. Which he doesn't like for some reason. I just didn't save everything, I see. Okay, bad news. That fan's not rendering. Render fan. GL triangle fan. Did we do this right? Oh, hold on. I forgot. Point source. Bind data, point buff. We have to do this every time. I forgot. If the lengths change, he gets upset. Oopies. Need to get to bed. Clearly my brain's getting up for the night. Good night. Thanks for the help. You were... I'm sure that it's frustrating to watch someone else do math shitty. I'm sure that that is frustrating, but I appreciate the help. Mostly there, we're just not rendering one of the triangles. So we need to append at the very end intersection point 0. If intersection points len is greater than 0. Okay. Out of memory, because this thing I said 9, and he needs 10 now. So true. Oh, come the fuck on, dude. Come on. Come on, man. Look at that. Look at that shit. Look at that. What if we make the blue one too big? Oh, come on, man. Oh, this isn't good. There's a bug here. I think we're missing one iteration here. We probably have to do the left edge twice or something. Oh, left, top, right. Oh, you're right. I just do have 2 left feet. Top, left, bottom. You were just right the whole time. Okay. Rotate this around. Nice. Let's make this guy bigger now. Rotate him around. Cool. Offset, offset. I guess we probably should test like 0 overlap as well, right? So kind of like just bring him up here. Yeah, dude, that's kind of fucking sick. Didn't know math was this sexy. Hell yeah, dude. Any like degenerate cases that we haven't tested here? I think it's like looking mostly kind of right. Hell yeah. Yeah, so we've tested fully inside both, fully outside. What exact overlap? Yeah, I guess, huh? I don't know if I can like enter this here easily, but we can try. X. Oh, we actually should because they move in nice even increments. So x0, y0, rotation 40. I guess we'll just try to match this on the other side. So 0, 0, rotation 0.035. Oops, positive. 035, and then we have 8 and 830. Looking pretty good, man. Looking pretty good. That's kind of fucking sick. And so if we're trying to calculate intersection over union, now like the math part of this is easy, right? All we have to do is basically take that triangle fan that we made and add up the sums of all of those triangles, add up like the areas of all those triangles, and that gives us like intersection size. And then union size is just the 2 boxes minus the intersection. Which is fucking easy. Fucking easy. All right. Quick 15-minute job. Yeah, I mean, so the thing is that the rest of it, like, I kind of like fucked myself a little bit here. In that I implemented this all in Zig on CPU. Where this actually is going to be useful is in Zig on GPU, or sorry, in OpenCL on GPU. Because what I actually need this for is for calculating bounding box overlaps for the AI stuff. So I'll probably do like the area calculation there once I've like migrated everything over. Fucking easy like line intersection. Dude, I can't believe how long that line intersection took me. It's like way harder than I thought it was gonna be. But anyways, okay, cool. I'm happy with this. Thanks for watching, guys. If you like what you saw, we stream most days. We aim for 12:30 to 4 o'clock Pacific time. It's just before 4 now. So anywhere between like 3.5 hours ago and 15 minutes from now is when you should expect to see us live. we're working on this like neural network training framework with the end goal of doing like barcode scanning on my phone in a web page. So if you want to see, all of that stuff, there's a YouTube link in the Twitch description with like a neural network playlist in there. Some stuff, most of like the feature development goes up there. But some stuff does not. The stuff that does not is like not really important for you. It's, how do I say this? I think it's interesting still. It's work that needs to be done, but not necessarily stuff that is easy to title and thumbnail or like is worth posting on YouTube every day, because like the YouTube algorithm is fickle. So stuff like cleanup. Today it was like making this GUI for the prep for this main segment of the stream, as well as we did a little visualization on this guy. Look at this. Look at this shit. Check out this sick barcode correctness visualization. Look at this. So we can see on our training here that like the barcode, it got most of this barcode right, but this part right here, it was not sure about. The actual value was supposed to be dark, but he was like a little gray. So, that was like just a little bit of like side work of like GUI stuff. We didn't actually like implement anything new, but it was like some visualizations and cleanup and stuff. So if you want to see stuff like that, that goes on Patreon or YouTube members or in Twitch VODs. And if you pay in the appropriate place, you get the knowledge of knowing that you're helping extend the lifetime of the stream. And also, you get the VODs that we don't post. But okay, that's all the plugging. Thanks for watching. YouTube, peace out, and Twitch, let's find someone to raid.